Hello. With an introduction like that, it's hard to live up to. But as Ilaria said, my name is Peter Van Kirk. I attend Suncoast High School. And this summer, I had the pleasure of working in the Astuda lab on the mechanical engineering track. So the Astuda lab focuses on studying synaptic plasticity. It is thought to be the underlying cause of learning memory. And my project in particular focused on functional brain mapping via intrinsic optical signaling imaging. I'm sure that sounds very confusing. So let me first break it down by defining brain mapping. Brain mapping focuses on determining both the location and function of neurons in the brain. Take, for example, the brain mapping is allowed for a better understanding of how the brain works. So take, for example, the occipital lobe, which we now know controls visual perception. Brain mapping is performed using a variety of techniques. In my lab, we use a technique called intrinsic optical signaling, or IOS. This is where you first stimulate a subject, say, shine a light in front of their eyes, and then observe the changes that occur in the brain tissue. There are a variety of different stimulations that can be performed on subjects, such as olfactory stimulation, which is stimulation by sense of smell, auditory stimulation, or even sotomosensory stimulation, which is stimulation by touch, pressure, or temperature. My lab in particular uses an airbrush to puff a gust of air towards the mouse's whiskers. This is similar to taking a brush and brushing along the hairs of your arms. As for observing the brain tissue, we use an LED green light to shine red and green wavelengths onto the brain. As you can see here, LEDs are fastened around the microscope's objective. Different wavelengths have different interactions with the brain tissue. In particular, we use green and red LEDs. So here you can see that there's a baseline at -10 seconds. This is where we're just recording the brain tissue without any simulations or any lights. And at 0 seconds is where stimulation begins. And then at 14 or 10 milliseconds, you can see some brain activity starting to show up. And what we're actually measuring here, what we're actually seeing, the reflection, is the changes in calcium and total blood volume. So these represent an increase in brain activity. And these wavelengths actually show a different reflection when there's an increase in calcium and total blood volume in this brain tissue. So for the previous system, we use an airbrush, like I just said, and a microscope and an LED. The mouse would be sitting right here. And the problem with this system is that it actually had a few issues. So the system had inconsistent lighting because the LEDs around the microscope wouldn't actually show on the brain tissue. It would be showing around the brain. So it wouldn't actually light up the image, which is what we need to do to see the reflections. Secondly, it had a very low stimulation frequency. So it maxed out at whatever the air compressor could actually perform. And that was at 4 hertz. And we were trying to achieve 100 hertz for our experiment. And lastly, there were some setup problems. As you can see, there's Play-Doh here, and it's used to stick the airbrush along the microscope. It's very hard to actually stick it and aim it at a whisker. This is a very small nozzle, and aiming it at the whisker is very difficult to replicate every single time, which is what you need to get consistent data. So I was tasked with solving these issues. Firstly, I went to the drawing board. Please forgive me for my art skills. They aren't very skilled, but as you can see here, I have a motor and a hook attached to it. It would just rotate very lightly and do a light push and tug on the whisker. So this would be used to stimulate the mouse's whisker. And then I made a case in SolidWorks. SolidWorks is a CADing software, computer-aided design. As you can see right here, I have a hole. This hole is used for a zip tie, so you can actually fasten this case to the microscope. And there is also curved edges on this case because if you have any experience with 3D printing, if you have a solid edge, it's actually very difficult for a 3D printer to print this. So it takes more time. By having these curved edges, it actually reduces the printing time. Additionally, I had to make sure that I oversized this part when I was printing it because 3D printers tend to undersize parts. So here you can see the final product. Here is the zip tie hole that I mentioned earlier and a hole in the back for the wires to go through for the motor. As mentioned in Michael's presentation earlier, he used an Arduino IDE, which is used to program the TNC 4.0. But he actually, something he didn't mention was that he used an Arduino to begin with, and then he transferred over to the TNC 4.0. What I used in my project was an Arduino Nano. It is a smaller Arduino. And again, Arduino is just a tiny processor, like a tiny computer, and it's programmed in a C-like language. The motor that I used for my project was a servo motor. This motor has a very low torque, which is the rotational force. So it's not pulling or pushing on these whiskers very difficult or very roughly. It is very light and it has a high frequency, which is exactly what we needed for these experiments. And lastly, here you can see a video of the motor actually working. And I did actually change the design to a pipette at the end because I found out that the musical wire that I was using to use as a hook was actually more difficult to get it to stay on the whisker. It was easier just to have it in a pipette. So the ring light has to be attached to the microscope in some way. The original design was a ring of lights around the microscope. It was actually too small. Like I said previously, if you take the exact dimensions and put them into SolidWorks and then 3D print them, it will be undersized. And as you can see right here, there is actually a crack in the part. This is because when you put it on the microscope objective, it was too small and it just cracked. So to solve this, I helped create a second ring light. This one actually has the proper dimensions and it did not break. However, there were some additional problems that were introduced here. The prongs were actually too close together. So if you ever have experience with soldering, it's very difficult to solder these parts together because if you cross the positive and the negative, you could actually short the bulb and then you can actually use the bulb, or you could even attach the red and green LEDs on the same wire, which is not what we're trying to do. We need to have the red on a separate one and the green on a separate one so we can test them separately. So I created a third design. This one actually has pipes going out the top and you can actually bend the prongs. So you can bend them outside the top of the pipe and then solder the wire across accordingly. There was an additional problem with this though. Like I said earlier, the images had inconsistent lighting. And in order to combat this, I created a fourth design, which actually has the holes at slants. So the LEDs come out at an angle instead of going directly down, and it actually shines on the brain instead of shining around the brain. As for system comparison, the old system was not replicable or sustainable, and it had a very tedious setup with that airbrush. It was also very difficult to tell when stimulation actually occurred. With the new system, it was 1% of the original system's cost. I'll let that sink in. It had no false stimulations. It was highly customizable for experiments, and it was very easy to set up, again, just a zip tie. And it had a 3,200% stimulation speed increase, which is very important because we were trying to achieve 100 Hertz, and my machine can actually achieve 1,000. So as for the importance, again, as I mentioned earlier, the Pseudo Lab is researching synaptic plasticity. This is the changing of dendritic spines over time. As mentioned in Ariel's presentation, she went into details in dendritic spines. But again, just to recap, they are the communication between neurons, and the synapse connection actually changes in strength over time. So they change based on the usage. So let's say you have a password on a computer. If you have it on autofill and you type it in once and you never type it in again, it'll be very hard to recall this password later on. But if you type this in every single day, say like your password for your computer just to get in, you could probably recall it pretty easily on the spot. So the more you use it, the more it becomes easier to remember. And all this research is actually helpful for understanding learning and memory disorders because with this research, we're learning more about learning memory, as I just said. This is actually the changes that occur in the brain when you learn something or when you create a new memory. So it's very useful. I'd like to thank the Pseudo Lab, Dr. Long, Nicole Daniel, Dr. Laurie Drago, Erica Eggerman, and my fellow interns for giving me an amazing experience here at Max Planck. And one big final thank you to the Max Planck supporters who made everything possible. Thank you. Are there any questions?
Great job, Peter. Did you said yesterday about the 100 Hertz and 1000 Hertz? Did you add it?
Yeah, actually, yeah, I did just because it was,
It's like they are adding things last minute. Questions for Peter?
Simple question. Did you learn soldering there or did you have the skill already before?
The question was, did I learn soldering here or did I have the skill already before? I actually had learned soldering from my robotics team. I'm a part of First Robotics, and it is a very helpful outreach to the youth community. I learned soldering there, and I've experienced it, or I've had some experience with it for about 4 years now. Yeah.
Michael wants to pay it back.
The apparent defect with the 3D printer, I'm surprised someone hasn't solved that issue so that you don't get that you would get full size reproduction instead of having to, is it guesswork to get to what you were trying to attain?
Yeah. So the question is, why hasn't someone solved the problem for the 3D printer underprinting parts? And to that, I say it is kind of an industry standard at this point that people just assume 3D printers are going to underprint the parts. There hasn't been much of an effort to actually fix this because many of the people who use 3D printers just kind of already know about this. So it would kind of be like switching back to a way that would add more complications if you switch back. So people would, you know, have oversized parts for a little bit and then they finally figured it out. But yeah.
Maybe you mentioned this and I apologize if I missed it, but why the 100 hertz stimulation if rats palpate at much lower rates, like closer to 10 to 15 hertz?
So the question was, why do we use 100 hertz stimulation as opposed to 10 or 15 hertz? We're actually reproducing a previous experiment, and in doing so, they actually went for 100 hertz. I don't know exactly why 100 hertz was the exact specific amount. I could ask my mentor later on and get back to you, but yeah.
Hi, great talk. So my question is, how do you synchronize your sensory stimulation with your neural recordings?
So the question was, how do I synchronize my sensory stimulation with the actual recordings? And I actually added an LED light that flashes a second before the simulation occurs. This flash shows on the video just as a flash, you know, an increase in light. And from there, the viewer can create the baseline at 1 second. And then 1 second after that flash, the simulation actually occurs, and they know how far off the activity is from the simulation.
All right.
Your ring light, you used red and green LEDs. Why red and green?
The question is, why do I use red and green LEDs on my ring light? And the answer to that is red and green have the reflections on the brain tissue actually show when there's an increase in calcium or change in the total blood volume. Those specific wavelengths have interactions with the brain tissue. So we actually have to use those wavelengths in order to notice the changes in the brain.